Simple harmonic motion. All right, we're going to start a new unit. It's simple harmonic motion. And I started here with a definition, and it's pretty simple. It's when objects vibrate or oscillates, and I like to use that word oscillates more, back and forth over the same path in each oscillation taking the same amount of time. So the best thing to do is to give you an example. We're going to start with a mass on a spring. So I found a diagram here, and I'm going to explain to you how it works. So I have a mass, and I attach it to a spring, and the mass comes to rest. And the position where the mass comes to rest is called the equilibrium position. E-Q-U-I-L-I-B-R-I-U-M. Equilibrium position. And then I have to put in some work. I have to either force the mass up and compress it, or I can force the mass down and stretch it. And the amount I compress it or the amount I stretch it, that position from equilibrium is called the amplitude. And for the spring, the amplitude is measured in meters. So let me go ahead and give you the definition. For amplitude is distance stretched or compressed from equilibrium. All right, and so once I put in that force and then let the mass go, it will begin to oscillate. So if I place a force in this mass and compress it up, so my force is up, then I let the mass go, it'll begin to fall. It'll fall through equilibrium down to a maximum stretched position, and then the direction will change. It'll oscillate back up through equilibrium to the maximum compressed position where I started it from, and then it'll fall back down, and it'll complete this motion over and over again until it starts to slow down due to friction and air resistance, which we call damping. And we won't get into that too much. All right, so I have to place a force into the spring to get it going. The amount of force I place into a spring to either stretch it or compress it depends on two things. It depends on the distance I want to compress or stretch it, and it depends on the nature of the spring. How stiff is the spring? And we have a value that basically describes the spring, and it's called the spring constant. Spring constant. And it describes the nature of the spring. Describes the spring. And the symbol it's given in an equation is K. So if K is a very large number, then that means that the spring is really, really stiff. And if K is a small number, then that means it's a soft spring, and it'll stretch quite easily. And so we have to look at two things. How much do I want to stretch it or compress it? And what is the K value? How stiff is the spring? And we have an equation to define that, or to calculate how much force, and it's called Hooke's law. Hooke's law. And it says F is equal to negative Kx. K being the spring constant, and X being the amplitude. That is the distance stretched or compressed from equilibrium. And this negative sign is a direction. What it's saying is that if I force my spring up and let it go, the displacement will be down. So that's where that negative sign is. If I pull my spring down and let it go, then the displacement will be up. So that's really all that negative sign is there for, is to designate the direction that the spring is going to move. And so F is proportional to K and to X. If X is high, then F is high. If you want to stretch it a lot, then you have to place in more force. All right, so let's talk a little bit about what's happening. Well, I think most of you are either in pre-cal, or if not, I'll go ahead and explain. what happens is when you place a force on this mass and set it in motion, it's going to oscillate up and down, and it's going to create this sort of sinusoidal wave. And then what we're going to do in future labs is we're going to graph this position, and I'm going to ask you a few questions about what exactly is going on at certain points in the position. But so I can say that if I start from here and I press up and it stretches down and it comes back to the original position, that is one cycle. All right, so one cycle is how far it goes up, down, and back to its original position. If I start here, then a cycle will be down through equilibrium to maximum stretched, back up through equilibrium to its original position. So that is a cycle. And the unit for a cycle is a hertz. And I hope some of you know that, H-E-R-T-Z. And the symbol it's given is an F. Now, the time it takes for a cycle to occur is called the period, T. IOD, time for one cycle. And the frequency is actually the number of cycles in 1 second. And they're inverses of each other, S-E-C-O-N-D. And they're inverses of each other. So T is 1 over F, and F is 1 over T. So if it takes a cycle 2 seconds, then the period is 2 seconds, and the frequency is a half, because that's how much of a cycle will occur in 1 second. I'm sorry, I don't even have any of this in the screen. Let me go ahead and slide that up and give you all a chance to copy that down. Sorry if I'm sniffing, but my allergies are acting up. Okay, so let's go back to what's happening on this spring. Let me see if I can position this a little bit better. One of the things about simple harmonic motion is it is subjected to what we call a restoring force. A restoring force in a spring system is in the spring. That's where the force comes from. Once you get it started, then it's going to restore itself and repeat this cycle, or this sort of sinusoidal wave over and over again. Restoring force. All right, so that's the spring. And later on, we'll come back to all kinds of equations, and I'm sure we'll all have fun with that. So after the spring, something else that will exhibit simple harmonic motion is a pendulum. So there we have a pendulum. And believe it or not, if we graph the data, a position versus time for a pendulum, it'll produce the same sine wave, a sine curve. Except we have a couple of things that are a little different here. In a spring, the amplitude is measured in meters, but in a pendulum, it's measured in degrees. Amplitude in degrees. Okay, and one of the things about a pendulum is it will exhibit simple harmonic motion for small angles. It's such a thing called a small angle approximation. And the key is that you have to keep whatever this is hanging on taut. So when you get to larger angles, the tension in the string tends to fall out. And when that happens, it won't have this smooth back and forth motion that harmonic motion has. The restoring force in a pendulum is actually gravity. So once you put in the work and pull that pendulum back to some angle and let it go, then gravity takes over and it causes the pendulum to swing back and forth. And a cycle for a pendulum is from the starting position through equilibrium back to where it started. That is the definition of a cycle for a pendulum. I think that's about it. That's a good introduction. I'm running out of time. So watch this video, and on the next time I see you, we'll probably have a lab. So I hope you understand this, and I'll see you next class period.